So last time we were given a function, we wanted to talk about the domain and range. And this, I want to go back over that to clear up any possible misunderstandings, or it's easy to get the wrong idea when we start drawing graphs. I have a way of thinking. There's a few ways of thinking about this, and I want to try to present this in the following way, because I think it might help clear up any misunderstandings that we have. So, okay. I have defined a function right here. F of x is equal to 2x minus 1. Now, we see that that's a line because we've been working with lines for years now, right? But for right now, we're going to forget that it's a line, and let's just investigate some of the inputs and outputs that would happen from this guy. Now, remember, a function is a rule. It's just a rule which tells us where an input goes, basically, right? So let's do that with a couple of them. Now, I'm going to ask you, when the input is minus 1, what is the output?
-3.
-3, right? Because -1 times 2 is -2 minus 1 is -3. So pictorially here, or using this idea, I'm representing the inputs in green, I'm representing the outputs in red, and then the function itself is blue, right? And this is pretty abstract. The function represents the rule, right? The roadmap for how to get from your starting point to your ending point. So let's do a few more. When I plug in, oh wait. Yeah, all right. -1 goes to -3. All right. Now, what about 0? Where does 0 go?
To -1.
-1, right? Plug in a 0, makes all of that disappear. The only thing that's left is -1. So 0 maps to -1. Okay, what about 1?
So 1.
1 goes to 1. Plug in a 1, you get a 2. Minus 1 gives me 1. Okay, so there's that. Finally, let's do one more, 2. When I plug in a 2, what is my output?
3.
3. Okay, so this right here is how this is a great way of thinking about a function. We've just taken a few numbers, we've mapped them to new numbers. Now, let's kind of round this off here with a graph. So a graph is the same thing. We could say for any input x, we're going to call our outputs y. Like, I don't like that. I'm going to call the outputs f. Just because like we're calling that thing f, we could call it y, but we're going to say the value of f. Okay, so now I'm just going to recreate what we did here. Actually, no, before that, let's forget about that. And let's just say, well, wait a second, that's a line, right? Like y equals mx plus b, in which case I would know that the y-intercept is what?
-1.
-1. What does that mean? Well, the y-intercept, or in this case, the f-intercept, sorry, we're talking about where does this thing go through this line. And anytime you're on that line, I don't care if you're here or here or here or here, the x value, the input value, has to be 0. So we can say, well, when I plug in a 0, that becomes 0, and my output is -1. So we know that this guy would go through here at -1. And what is the slope of this line?
2.
2, because that's the number in front of x, right? So we could say the slope is 2. Means the rise over the run is 2, which means that if I run, let's say 1 over, I go 2 up, right? So if I go 1 over, I go 2 up, it should look something like this, right? And so I'm going to go ahead and draw my line through here like this. Now, okay, so that is what we know about drawing lines. We've been doing this for some time now. And let's try to marry these two concepts together. Okay, so when it comes to inputs and outputs, this thing that I drew, I wasn't really, well, I guess what I was talking through were just the rules that we've learned thus far for how to draw a line when it's in slope-intercept form, right? Well, let's think about what we've really done here. We said if you take an input like -1, which would live right here, we take -1, the output we get, yeah, that's right. The output that we get, the output that we get is -3. Okay, it says that when we plug in a 0, the output that we get was -1. Right? Here is a -1. It says that when we plug in a 1, the output we get is 1. So when we plug in a 1, the output we get is 1. Is that right? Yeah, that is right. Huh. Interesting. What we get is 1. Okay. Finally, we plugged in a 2 and we got out a 3. So that says when I plug in a 2, my output is a 3. It's a little longer. So, okay. Oftentimes, and I think this is where a lot of the problem comes from when trying to marry these concepts together, or trying to think about the graph of a function in terms of its inputs and outputs. We often think about this line itself being the outputs. But this line itself has nothing to do with the outputs. Rather, what it does is it gives us a roadmap for how to get to the outputs. That's why I've kind of color-coded here, right? The blue line is the same thing as these blue arrows right here. And the way we do this is we say, well, okay, this right here, this roadmap tells me that when -1 is the input, I go to the roadmap, right? And it tells me that I need to go to -3. When I'm at 0, this rule tells me that the output goes to -1. When we plug in a 1, the roadmap says go this way, right here. When we plug in a 2, this roadmap says then we go to here and go to +3. And so, yes, we could think about this as being a set of points that's kind of out there in space somewhere. But what's really happening is that we're taking this, in this case, I've only done from here to here, right? I've taken an interval and I've put that interval into a function. And then we get a new interval out of that, right? Given these inputs, we get these new outputs. And we could actually make this a little better and say, well, what if instead of just these 4 numbers, I included all of the points in between them? And that's kind of what we're doing, what we're set up to do here. Is like, if I take all of the numbers between -1 and 0, and treat them as inputs and evaluate each one of those, well, what's going to happen? Well, over here, this picture kind of tells me like, well, if -1 goes to here and 0 goes to here, I'll bet, not 100% sure on this with the way that I've drawn this, but I'll bet you that all of these guys are going to hit every one of those, but every one of the red points between -3 and -1. And this is right, now this is where this picture starts to break down. It starts making less sense, and it's like, well, this is kind of nice because I could see by after drawing this line, like, yeah, that's what this means. When I take these points here and plug them into the function says, well, this point right here gets mapped to this point right here. And so on and so forth for all of these other points, right? We could say, okay, these go here, this one goes here. And indeed, that's kind of the picture that starts to emerge. When I take this interval, in other words, all the numbers from -1 up to 0, plug it into that function, then the output that I get are all the numbers between -1 and -3. So that is what's happening here. And so again, as I continue on, it's like, well, let's see what happens. When I plug in all the rest of the numbers, when I'm going to say from 0, all of those in between and all of those in between, it looks like from over here, we're going to hit all the numbers in between here. And indeed, that's what happens when I take all the numbers from 0 up to 2 and actually plug them into this function. The rule says, well, here first, you start going down here, right? If it's between 0 and whatever number that is, then it tells me that we map them onto here, right? So inputs here. Function says map them over to there. And so that's what we get. We get this little interval from here to here. And then as we go on, right, we get these guys get mapped up here. These guys go here. These guys go here. And so finally, what we end up with is we find, and we're going to do this in symbols in just a second, is that when I plug in the interval, we could say, and there's another way of drawing it, what we just found, is that when we take the interval -1 to 2, and I guess we'll go ahead and include the endpoints. The function f maps that interval. It takes that interval and just kind of stretches it out, right? It says, when we plug in this guy, the interval we get out goes from -3 to 3, like that. And so, if I were to say, and this is the thing, right? When you look at that function right there, and I'm not talking about inputs yet or anything like that, if I were to say, what's the domain of that function? We'd say, well, we said this last time, it's all real numbers, right? There's no problem taking any real number, multiplying it by 2, and then taking whatever you get out of that, subtracting 1. The entire thing is the domain. And that's cool. And usually that's what I'm going to do. I'll ask you that kind of question. But later on, when we start talking about, say, models, which is where you write a function to describe something in the real world, right? Like, let's just pretend right now that this function describes, I don't know, your company's revenue in millions of dollars where X is the number of days before or after today. What this would say is like, well, yesterday at -1, I lost minus $3 million, right? Something like that, right? And it would say like, and one day we could expect that my company would gain $1 million. 2 days from now, my company will gain $3 million. There's some kind of relationship there. But in the real world, whenever we have a model like that, it usually breaks down at some point. This trend is not going to continue on forever. You can't say in 5 billion years, how much money can you expect your company to get? That doesn't work, right? There's usually some amount of time where it doesn't make sense anymore. And also in the past, maybe I started my company yesterday. It wouldn't make any sense to ask, well, how much did I make 4 days ago? Well, your company didn't exist. And so in the real world, our domain isn't necessarily determined by the function itself. It's more like the context of the problem that we're working on. If I started something yesterday and I know my model isn't going to work after 2 days from now because I just can't predict that well. I don't know what the weather's like or whatever, but I'm fairly certain that it's good yesterday, that this model right here, this prediction was good yesterday, and it'll be good for another 2 days or so. Then I might say, okay, then this function is defined on this interval. And then this interval becomes the domain. Then I could ask a question. And so that's what we're going to see, right? And I might just do that at any time. I might say, this is a function. It's defined on this interval. That means what I just said there is that I tell you that the domain of f is equal to -1, 2. What I've just said is, for whatever reasons, this makes sense when we're talking about yesterday and 2 days from now, but it won't make sense otherwise. So we're only going to define the function for here. So these are my only allowable inputs. Then we could say, well, if that's the case, if those are the only allowable inputs, then what's the range of f? And if we remember our definition from last time, we say the range is what you get when you plug in all the allowable inputs. And what we've just done here is we've seen that. We've seen that the interval -1 up to 2 maps onto this new interval, -3 up to 3. And this is where this picture just starts not making sense. And so we want to try to move ourselves into this picture where we're thinking about that line that we drew. It's not really a thing, right? It just tells us how to take this old interval and turn it into a new interval here. And I would say then in this case, given that that's my function, and given that we're only plugging in values from here to here, then my range would be this guy right there. And how would I find that? Well, I would, honestly, there are a lot of ways that we could do this. We could do it with inequalities and absolute values and all that kinds of stuff. But what we're going to do in our class is we're going to draw us a graph. And we're going to say, when these are my inputs, those are my outputs right there. And you might be saying, yeah, but Justin, this goes on forever. And it goes on forever in that direction. We could keep plugging stuff in, and it goes on forever in that direction. We keep plugging stuff in. I'm not worried about that right now. Because what I've done is I've defined the domain. I've told you these are the only inputs we're concerned about. Therefore, you tell me what are the outputs that we are looking at. This is the relationship. And so that's what this is, right? We like to think of this blue line as a thing in and of itself, when really all it is it's just a map for us to be able to say, yeah, that's how you get from point A to point B.
And if you have a defined domain like that, then your line shouldn't go on forever,
It
right?
shouldn't go on forever, right? Because we're saying we're only putting in those inputs. And so if I've told you graph this function on this interval, it should only, thanks, buddy. It should only look like that. Good question. Good question. Yes.
Okay.
All right. Hi, buddy. I got to teach some math now. Okay, so we got more to do. So, okay, are we ready to move on?
Yes.
Okay, I'm gonna go ahead and erase this stuff right here. There. Yeah. All right. All right, domain range, we have done that. So lines are functions. That is how we are going to think about lines from now on and forevermore. We are going to think of them as functions. Now, clearly the way I've written it implies that when you see it like that, right? But when you see something like this, how about 3x plus 2y equals maybe 1, that does not look like a function to me, right? And what do we, now let's say I gave you this and I said, I want you to graph this. What would you do?
I would convert it into standard notation. Or that's what it's called, I think, right? Standard notation.
We could call it that. I think slope intercept form is technically what we call it because, right, we have it whereas slope and then an intercept. But yeah, if we want to call it from now on standard form, I like that because that's what we're always going to do, always and forever in our class. We're gonna, so what I mean, lines are functions. This defines a line, yes, but it doesn't look like a function. Why? Because a function tells me how to compute an output given an input, right? And so what does that mean? Well, if my y's are outputs, which they're always going to be, right, then we want to get y by itself in order to find out how to do that. And just like you said, right, we want to put this into slope intercept form. So how do I do that? You tell me what to do. What steps would you take if I told you to take that and put it into y equals mx plus b?
Well, you could subtract 3x from the first section from both sides.
Both sides, right? Because we have an equation, we got to do that. The only reason I did that was to get rid of that guy. And so now we have 2y equals, and I'm going to go ahead and write it in the way that's going to help us out in the end. Minus 3x plus 1. Now what do?
Then you divide by 2.
I'm going to say, yeah, y, we're trying to get y by itself. Y gets multiplied by 2. The opposite of multiply, or the inverse of multiply, is divide. So we're going to divide by 2. So that means I got to do it to everybody over here, right? So I'm going to do it over here and over here. We could have put the whole thing over 2, but we're ultimately trying to get to something that looks like that. And so that's how I'm going to do it. So I'm going to say, okay. That number right there is minus 3 halves x plus 1 half. And now we have a line in slope intercept form. But more importantly, this is now a function, right? We could think about this as saying whatever output you want, you go minus 3 halves times your input plus 1 half. And so this thing is now a function, right? So real quick, let's do this. So I'm going to continue to keep this guy right here. And I'm going to even, I'm going to replace this y with a y of x. I'm going to say y of x. So that now we're getting it into our minds like, yes, this thing is a relationship between inputs and outputs. It's not a geometrical object that I'm drawing in space, although we could think about it that way. It's going to be much more useful to us if we think about it as a relationship between inputs and outputs, which is what the y of x implies right there. Okay, so I'm going to draw this guy real quick. Say, all right. That's pretty easy. Where does it go through? Rather, what's the y-intercept?
1/2.
1/2. Now, there's a couple ways we could do that. We could just remember from, before, like, well, my book says that when it's in this form, this is the y-intercept. But I'd much rather think about it like this. I'm going to say, well, the y-intercept means wherever it crosses the y-axis. And so what that means, y-intercept, is when, I'm going to use this term when a lot. And I'm going to say either when or where. And what we're talking about is when, or we mean where on the x-axis. We also think about the x-axis as being time often. And we think about time going from left to right. And we could think about, oh, when did something happen? I think about a little stick figure running across that axis. There's a speed line, so you know which direction he's running. And you can think about, you start a stopwatch when he's here at x equals 0, and then you want to know when does he get to whatever. So I'm going to use that a lot. The y-intercept is when what? Well, we're talking about some function or some line going through the y-axis. Well, what is the x value if you're on the y-axis?
0.
It has to be, right? Is when x equals 0. Well, hold up. I have a relationship between y and x. So I could say, well, then the value is whatever f of 0 is. Right? And so looking at this as a function, I'm just saying, okay, well, let's just plug in a 0, y of 0 equals, and 0 is one of our best friends in this class because it usually makes things a lot easier to deal with. I can see that this times 0 is going to be a big fat 0, and we're left with, well, whatever's hanging out at the end, which is actually the part that we call the y-intercept. It's called the y-intercept because of this, right? So I'm going to say, okay, we're up here at 1/2. In other words, this is the output value whenever x is equal to 0, or in this case, we have y of x, y of 0. That's the output we get when that happens. Okay. Similarly, this is a relationship between x and y. So if I want to know the x-intercept, I could say, well, the x-intercept is when what? So a function crosses the x-axis. Say it.
When y equals 0.
Y equals 0. There's this nice symmetric relationship, right? And let's look at it, right? I don't care where you're crossing through the x-axis. It could be over here. It could be over here. It could be a bunch of times over here. Whenever you are on the x-axis, your y value must be 0. So the x-intercept happens when y equals 0. So in other words, so here's the y-intercept is when that happens. Its value is that. And in order to find the x-intercept, well, we say that y equals 0. So 0 equals the output value, which is y, which we're going to think about in this case as y of x, but in general, some function of x. In other words, what I'm saying is set f of x equal to 0 and solve for x. So let's see what that would look like here. I'm going to say, okay, there is my relationship. There's my relationship, and we're going to say the output value, right? The y value itself is equal to 0. Well, what does that do? Well, that's minus 3 halves x plus 1 half. Okay, how would you go about solving that? What would you like to do?
Hold on.
There's no wrong way here. I could think of about 50 different ways to start. And whichever way you're most comfortable with, what would you do to solve for x for that equation right there?
X plus 1 half. I would probably add 1 half to the other side and then, oh no, wait.
Add 1 half?
No, I meant subtract, sorry.
Right. We put it on the other side. Yeah. So let's do that. In fact, I'm going to start a little bit higher here. So 0 equals minus 3 halves x plus 1 half. And yeah, right. And that's kind of how I think about it. Like my mind says, I need to get that guy by himself. And so then that's the first thing that happens. It's kind of like you put on your socks, then you put on your shoes. In order to get back where you started, you take your shoes off first, then you take off your socks. And so when I look at that, I see, well, what happens to x? Well, first he gets multiplied by that. Then he gets that added. So we need to undo that first. Those are the socks. Those are the shoes. Let's take off the shoes first by moving this guy to the other side. So now we have minus 1 half equals minus 3 halves x. Now, what do you like to do for this? There's, again, we could do this 5 different ways. What do you want to do?
Could you just divide by -3/2?
We could do that. That's exactly, because like what happened to x? X gets multiplied by a number. Well, if we divide by whatever number that is, that's going to get rid of it. So I like that. We'll do that. So divide by -3 halves, both sides. Divide by -3 halves. Okay, the whole reason we did that was to kill that guy, which he is now dead. He is gone. X. Now, I'm going to move over here real quick. Just want to give me some room here. We have -1 half divided by a fraction. What's the rule for dividing by fractions? Like, how do we do that?
I actually don't know.
All right, good. The rule is to divide by a fraction. It's the same thing as multiplying whatever's in the numerator by the reciprocal. So, right. So this is what goes through my head. I say, this stays put right there. And then I multiply by, instead of 3/2, -3/2, it's going to be -2/3. And so -2 divided by 3. That's that guy. Now, if we want to be, there's a few ways we could do this. We could go ahead and multiply everything on the top, multiply everything on the bottom. But right now I see something that cancels. And so I'm going to go ahead and knock that guy out and say, well, this guy's gone. That 2 and the 2 divided by 2 is 1. So we can get rid of it. The negative and the negative make a positive. So I'm left with a +1 on top. Divide by 3, and we get 1/3 right there. We just found that this quantity, -1 half divided by -3 halves, equals +1/3. And so that is the x-intercept. Right? Okay, so we're at 1 half and 1/3, and we have just found those points. And we say, okay, that's the line that goes through them. I'm not really interested in graphing the line. What I'm getting at here is thinking about this as a function takes a lot of the guesswork out of pretty much all of the problems that we have with lines, like what's the x-intercept, what's the y-intercept. If we could interpret this as a relationship between x's and y's, right, a rule which relates what x value for what y value, then we could say, wait a minute, y-intercept means when x is 0. We want to know what is the y value when x is equal to 0. Then we just plug in a 0, boom. Could say ditto with the x-intercept, right? And now, how much time do we have? Yeah, okay, we're gonna have to move on. So that's the idea with lines. If we're gonna think about them as relationships between inputs and outputs, it's gonna make things a lot easier. And now I'm about to tell you something that's probably gonna make your day. In your book, there are, from chapter 3, they give you, I think, the slope intercept form. They tell you that there's a point slope form for a line, and then there is a point, there's something else. There's like 3 different, there's the slope intercept, which is our guy. This is our hero of the story, slope intercept form. He's the one we're gonna roll with. There's point slope form, which is the equation of a line given a slope and a point. And then they have something else, which is like the point, 2 points line or something like that. And then there's, so at this point, at this juncture, we now have 3 equations to memorize. And I'm going to tell you, forget all of them except for point slope form. I mean, sorry, no, except for slope intercept.
Intercept form.
The y equals 1x plus b is all we need in our class, and it's all we'll ever need ever for lines. Everything about lines can be done like this, just as long as you're thinking in terms of functions. Let me give you an example, okay? So first off, can I get rid of all of this stuff so far?
Yes.
Okay, so. Okay, so. Here is a similar problem as to one that is in your book. It says given a line. No. We'll put it this way. Find the equation of a line with slope equal to, I don't know, let's say 3. Passing through the point. All right, buddy. Passing through the point. How about 1, 2? Now, the way that your book says to solve this is actually going to be quicker than the way I'm going to say to solve it. But the trade-off is that to do the book's method, we're going to have to always have in our minds 3 different equations. And then every time we're presented with a problem, we're going to have to stop and say, wait a minute, am I going to use equation 1, 2, or 3? Yikes. And then if you spend time trying to figure that out, and it's, sometimes you get the right one, sometimes you get the wrong one, and you think you're right, and then it ends up just going haywire, right? What we're always going to do is think about, we're only going to use slope intercept form. We're going to think about it as a function and watch how easy this becomes when we do this. Okay, so first off, this is the book's method. It says that there is an equation, and it's y minus y1 equals m times x minus x1. given a slope, which we have, and a point, x1, y1, we plug them into here. So we have to, first we read the problem and go, oh, right, and then we recall this formula. And now we're just plugging things into a formula and we say, okay, this value 1 is x1. This value 2 is y1, right, xy. And then m is the slope, so 3 is m. And now I'm plugging things into an equation and I say y minus y1 is 2. M is 3. And then we have in here, we have x minus x1 is 1. So x minus 1. Now, of course, that's not what the book is looking for. It wants it in the regular form that we always do, because that's the only way it's useful. So we have to distribute that 3. So I'm going to do that first. We get 3x, right? So the 3 jumps over the parentheses and hits the x, jumps over and hits the minus 1, so to give us minus 3. I'm almost there. I now need to get that y by itself, and so I add 2, so I plus 2 to both sides, and I get finally y equals 3x. Minus 3 plus 2 should be minus 1. And again, this doesn't mean anything in my brain. This is just something that I memorized and I pulled out, and then I had to figure out what that letter represents, what that letter represents, what letter that, and I hate it. We will never do this. And as of right now, you could forget this for the rest of your life. What we're gonna do is this. Here's the trade-off. So you gotta draw. Now you could learn how to do everything I'm about to do without drawing anything. But I'm telling you, with a guy with years and years of experience in math, like, drawing is your best friend. And at first it's a little, I know, like I was reluctant to get into it and to start to do it. And when I was taking Algebra 2, it was my most hated thing, but it's going to make your life so much easier. So here we go. This is what I'm going to do. The equation of a line with a slope that passing through a point. I know where that point lives, 1, 2. That's where the x value is 1 and the y value is 2. I know where he lives. Okay. And now he has a slope of 3. Okay. So that means it's going upwards, right? Now at this point, I'm not actually trying to solve it. I'm just getting an idea. So I don't know if it actually does something like that, or if it's steeper, maybe it comes through like that. It does not matter, because I just want an equation, right? The idea is find the equation of the line, right? So that's all I'm going to do. And I'm going to say, all right, so part 1 done. Now I'm going to say that this thing is my function that I'm looking for. That is y of x. That's my relationship between inputs and outputs. But that's the equation of a line. So then all equations of lines have this form. And this is the only thing we ever need to memorize. And we're going to use it in every single case. It's always going to work. It's your best friend. Love him, know him, become really familiar with him. So I'm going to write this down. And I notice, this is the key here, is that there are 2 things I need. I need to, if I know what M is, and I know what B is, then I'm done, right? That's my goal. So I've kind of written my goal here, kept that in mind. Okay, what can I do to find that goal? Well, first off, it tells me that the slope is 3. So most of my work, exactly half of my work is done at this point. I know that M equals 3. So I'm going to go ahead and write that down. M equals 3. Okay, that came from here. It told me. So now I'm just going to rewrite it and say, okay, well then my line that I'm looking for is 3x plus b. Now, this is the key. we know now this is a relationship between inputs and outputs. And I've already drawn this guy. I know that when 1 is my input, then 2 is my output, right? This is the function which maps 1 to 2. So in symbols, I know that when I plug 1 in, what comes out? Well, a 2. So now, thinking about this as a function, we've now taken this and said, well, hold up, what did we just say? When I plug in a 1, the output or the value when I do all this is a 2. So let's do that. I'm going to plug in a 1. We get y of 1 equals 3 times 1 plus my unknown b, which is the only thing I've left to find out. That's all I need to solve this problem. I know that when I plug in a 1, I get out a 2. In other words, 2 is equal to 3 times 1 plus b. 3 times 1 is 3. How do I solve for b? What's the last step here?
Subtract 3.
Subtract 3 from both sides. And I get that b is equal to -1. Okay. And so now that's the other part of the thing. Remember my goal said find the equation of a line. So immediately I said, okay, so I'm looking for this. That is my goal. Therefore, I only need 2 numbers. I'm only looking for 2 numbers. The first one is given, done. The second one, there it is. Now I can say, okay, m is 3, b is -1. So my original equation, y of x, mx plus b becomes 3x plus -1 minus 1. Boom. Now, at this point, you might say, wait, it looks like we had to do a lot more work here than we did over here. And I think this is just my conjecture that that's why they present this stuff right here.
That makes so much more sense.
But it does, right? It's like, well, wait a minute, what are we doing? Here, you're memorizing an equation and plugging in values, but it doesn't make sense what you're doing. And if you'll notice, we end up doing the same things in one as the other. It's just they're trying to make it easier on you by this. But what ends up happening is it's like now you're in equation overload, right? You're trying to remember all these different equations and you say, wait, when do I use which one? And wait, which one is X1 and which one's Y1? Which one? And then what we're about to do is when you have 2 points and you're trying to get this equation right here, then the equation goes off the wall and you're like, wait, which one's which and which one's that? Uh-oh. But this is what's nice, and what's really nice about this is then when we move on in this class and start doing the same kinds of questions for other functions that aren't lines, functions that don't have a nice simple formula for them, this exact same method is going to work for all of them. And then when you go on to take calculus, if you just know this method right here, you're going to be so much happier, because there's not a problem you can't solve if you're using this method. It works everywhere. It's always going to work. Now, I want to do one more example on this type of thing to show you exactly what I'm talking about. So can I erase all this?
Yes.
All right. So we want to find the equation of a line. Passing through the points 1, 2, and Let's do 2,6. Okay. The books method. Let's do the books method. The books method says, find the equation of a line passing through. Oh, I have 2 points. And so now I have to memorize I have to pull from memory the equation, which is this. In fact, we're going to need more room. Y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. And at this point, if you're not confused, you should be, because not only do we have y's and x's that aren't going anywhere, but now we have a bunch of y's and x's that actually symbolize the numbers that we're dealing with. Yikes. Okay, so what does it say to do? Well, we have to identify point 1 and point 2. We'll call this point 1, we'll call this point 2. So that means this is x1, this is y1. That means this is x2, this is y2. Now, what do we do? Well, y, which y? Oh man, I forgot there's like 4 y's up there. I think it's that y stays put. Yep, that y stays put. And now y1 is 2. Y2 is 6 minus y1 is 2. X2 is 2. X1 is 1. Okay. X minus x1 is, I'm actually confused. X1 is 1. Okay. Now, what do we do? It looks terrible, but I guess 6 minus 2 is 3. Wait.
4.
4, thank you. Keeping me honest. 2 minus 1 is 1. Okay. X minus 1. There we go. Y minus 2 is just y minus 2. Okay, so 4 over 1 is 4, x minus 1. The 4 jumps over and gives me 4x. Jumps over, hits the minus 1 and becomes minus 4. Okay, y minus 2. Add 2 to both sides and we get y equals 4x, I guess, plus 2. No, minus 2. Okay. Okay, that's the books method. My method, and we're running really short on time. I will actually, I think probably next time I will have a step by step, like step 1, do this, step 2, do this, step 3. So, but the cool thing is that's the only thing you'll ever have to remember. So step 1, draw a picture. Here we go. I can tell these guys are going to be here. There's 1, there's 2, and I don't have to draw this to scale or anything. Just as long as I draw it qualitatively accurate, when I plug in a 2, I get out a 6. And that's what goes through my head when I see this. Is like, I'm not thinking about these as y1s and y2s. We're thinking about this as an input to a function, output to a function. Input 1, you get out a 2. Input 2, you get out a 6. Okay, then this is a line and it has a positive slope. I could tell it's positive because it's going up. And when I imagine running from left to right, I imagine I'm running uphill. Okay. Now, okay. Step 2, actually step 1 should be write down the thing you want. This says find the equation of a line. So without using my brain, I'm just saying, well, the equation of a line looks like this, or it is that. Now I just need 2 numbers. One of them is M and one of them is B. That's all I need to do to solve this problem. So I draw my thing. You don't have to draw the stick figure if you don't want to. I like to draw, no, I'm kidding. So the slope I know is equal to rise of a run. And I'm not going to use a damn equation for that. I'm just going to use my vision and think, well, how high is the rise here? It's the distance from there to there. And in fact, what goes through my head when I think about that is if I had a ruler and I went to take a measurement of something that was this long, and I happened to move my ruler so that the 0 isn't where I wanted it to be, and I looked at my ruler and it read 2, 6 like that, and you ask me, how long is that thing? I would say, well, 3, 4, 5, 6, it's 4. The distance from there to there is 4. That's all we're dealing with is distance, right? Simply a distance. So the distance from there to there is 4. Similarly, if I took my ruler and measured from here to there, and my ruler said 1 and 2, I would say, well, that distance, the distance from 1 to 2 is 1. Okay. And so 4 is the rise. And then, so first I'm just thinking about distances. I'm not thinking about whether something's positive or negative. But I think if it's going up, it's positive, right? It's a rise over a run. If it's going down, then it's negative. It's actually a fall. It's not a rise, it's a fall. And so I would say, well, then that distance is a negative number. In this case, it's a positive number, so it's going up. And so I'm going to say, okay, the rise over the run is 4 over 1. We could reduce that down to 4. So m equals 4. Done. Now guess what we're going to do? Well, the way I like to do is I like to rewrite my equation once I get my new piece of information. And I'm going to say, well, now I could just plug in a number, right? We're back to where we were before, right? It's like I have an unknown, and I know that this is a relationship between x and y, and I could get rid of the x's and the y's by plugging in an x and getting out a y. So I could choose either one that I want. In this case, I'm going to choose the smaller numbers because it just makes sense to use the smaller numbers. If one of them happened to be 0, I would totally use that because 0 is our friend. But in this case, I'm going to say, well, when I plug in a 1, and this is, I'm not writing this down like this is part of my problem solving technique, but this is just what's going through my head is I know here that when I plug in a 1, I get out a 2. That is when x equals 1, y equals 2. So when I plug in a 1, 4 times 1 plus b, I get out a 2. All right, so I just basically, I took this right here, this idea that's in my head, and it said, yeah, whenever you do this, you plug in a 1 for x, the output, the thing you get, the final number you get when you do this equation, when you evaluate it, comes out to be 2. So my output is 2. So I get 2 equals 4 times 1 is 4 plus b. Solving for b, I'm going to minus 4 from both sides. And I get that b is equal to -2. And do I have anything left to find? No, my only goals were to find m and to find b. I have found m and I found b. Therefore, my final answer is y equals m for x plus a -2. So -2. And we're done. Way easier. I went into, I drew little rulers and stuff like that, right? And I kind of went in and I said this twice, but getting all of the redundancies out of the way. Yeah, buddy, boy, that's a loud toy he has. I'll help you in just a second. I'm almost done, big guy. Just a minute. So, does this make more sense?
This has never made so much sense in my life. This is crazy. I finally get it. I can actually see it.
And that's what I love, right? Is like when you think about what you're doing, and like notice all of this that we did is there. They're just trying to make it easier by giving you something you could plug something into. But when you do that, you've lost the main picture, right? All they're saying is that there's a line that goes from here to here. Okay, what's its slope? Well, it's this number minus that number. y2 minus y1, 6 minus 2. Yeah. And then it's this number minus that number, 2 minus 1. Yeah. But when it's just like this, you lose sight of what you're doing. And then this stuff, like we are totally out of time, but I'll probably do this in a quiz or one of the solution videos I post. I want to show you where this formula comes from. It's exactly what we just did here, but simplified, right? But when you think about this as a relationship between inputs and outputs, it actually, you don't lose sight of what you're doing, right? Sorry, I know we're going long. All right. Oh man, sorry, buddy. So I know we're going long, but I just want to show you one more thing that's pretty important. You'll notice that I chose to plug in when the input is 1, the output is 2. We could have, once we got to this point, I'm sorry, buddy, just give me a minute. So we could have said, well, what if, Justin, what if you had plugged that one in? Would you end up with the same thing? Let's just check that we do. So now I say that we'll get the same thing out if we plug in a 2 and get out a 6. So we could do that, right? Relationship between X and Y. Plug in a 2, you should get out a 6. And so I plug in a 2 and I get 4 times 2 plus my unknown B, which is the thing I'm trying to solve for, and I get out a 6. 4 times 2 is 8 plus B equals 6. Subtract 8 from both sides, and I get minus 2 is equal to B. And hey, what do you know? It's consistent. It works. Like, of course it's going to work. It had better work. Like both of, we started off by saying both of these points are on the line, so it had better work. But I just want to go through that to show you that we don't always have to take the first point like this says that we have to do. You could take the second point. It doesn't matter, right? And in fact, if I had given you these 2 points, or well, there's a lot of ways we can do this, but either way is going to work. If one of them is a nice point, like if one of them has 0 in it, and you know, like one is 0, 1, and the other one is 256, 599. Guess which one I'm going to work with. You don't have to choose the first one, right? I'm saying you could choose either one that you want. Okay. So yeah, that's my spiel on lines. We're always going to use this right here. And it's going to be easier, much, much easier if we just draw a little graph and plug in points and stuff like that. So any questions?
No.
All right, good deal. So Monday, let's have quiz 0.1 done. Now we didn't get to inverse functions today, and the last 3 parts of the last problem deal with inverse functions. I go, and the solutions are posted, so you could watch that. What I'd say is to take your best guess as to how you do it. Actually, let's just real quick. Do you have a minute? Can we just for a minute?
Yeah.
Okay. So just real quick for the last couple questions. I ask you to find the inverse of. I name 3 functions and I say find the inverse of them. We're going to go into this more Monday, like in greater detail. And actually, we might not, because if you watch the solutions video, there I go way into the method for finding inverse functions. But what is a function? Okay, so what are we doing here? This is a function. It is a relationship between X and Y. It looks like this. This is f of X equals 2X minus 1. I know that because when I plug in a 0, I get out a minus 1. It has a positive slope, so it goes up. Okay. Now, given any input X, I get some output Y. The inverse function is a function which tells me if I got out a Y, it tells me how to get back to X. Okay, So real quick, let's just think about what this function says to do. F says multiply by 2, right? Well, it says take x. It says give me any x and I'll tell you what to do with it. This is what you do. First, you multiply by 2. Multiply by 2. Then you subtract. And that's how you get your value. So if I plugged in, say, a 2, we would say take 2, multiply by 2, we get 4. Subtract 1, we get a 3. And my output would be a 3. Just a minute, buddy. Just a minute. So then what we want to do is like, let's just think about this. Now, how if I had 3 and I wanted to come back to find out the original, well, I would do these in the opposite order, right? Because this is like saying, first you put on your socks, then you put on your shoes. So to get back to normal, you have to first take off your shoes, then you take off your socks. And so to undo F, we will first, right? We got to do the last thing first. I guess the opposite of subtract 1 would be to add 1. Then the opposite of multiply by 2, to undo multiplication by 2, we would divide by 2. Let's just see if that works. We took 2 and F gave us a 3. Now let's see, if we have a 3, this says to add 1, so we go from 3 to 4. Then it says divide by 2. Yeah, we end up exactly where we came from. But so this is all an inverse function is. It's just it's a way, it's another rule that we have, but for undoing something we just did. But symbolically, how do we go about doing this really? So can I erase this stuff right here?
Yes.
Okay. Symbolically, this is what we do. Given f of x equals some formula, 2x plus 1, we pretend that there is an output value, and we're going to call it y. So this is like step 1. In the solutions video, I actually have the steps written down, but we say, okay, your output is y. Now, what we want to do is we want to have that rule for given a y, what do I do to get 2 back? In other words, I'm taking this and I just want to solve for x. That's the thing I want. I want a set of rules which tells me how to get back to my original thing. Well, what would we have to do? X gets multiplied by 2, then he gets 1 added to him. So I guess I will subtract 1 from both sides. Oh, does that sound familiar? Yeah, it sounds familiar, right? Now it's like, oh, okay. How do I get x by itself? Well, I guess 2 times x. To undo times, I go divide by. Okay, so now I divide by. And now I'm left with x equals y minus 1 over 2. And hey, what do you know? That's exactly what we just figured out. You give me your output, y. If it were 3, we would plug in a 3. 3 minus 1 is 2. Wait a minute. What did I do? Uh-oh.
The original equation was 2x.
Hey! My world just broke down. I was like, I swear this works. Okay. Man, thank you. Okay, so we'll do that again. Minus 1. There we go. Okay, so we say, okay, to undo this, so basically all we're doing right now is solving for x. Right? We're trying to get x by itself. And then we do this. Okay, and we have a formula. We have a rule which tells us given any output, how to get back to the original input. And let's check. 3 is an output. 3 plus 1 is 4. Divided by 2 is 2. And indeed, we get our original input back. So what we do is say this is a function. It's a function in and of itself. And there's its formula. And we write it, since it is the thing that undoes f, we call it the inverse. And its input values are the old output values. And so in this case, since I've called the output values y, I'm going to do this in terms of y. And so we get y plus 1 over 2, just like that. And that right there is the inverse of the original function. And technically we're done. We are done. The only little nitpicky thing is that we usually inputs to functions aren't y's, they're x's, right?
Right.
So we rename it and say, yes, this is a function and stuff like that. So we're just going to rename it and say, okay, this is x plus 1 over 2. Now, I don't go into this in the video, but you need to know this. Don't try to skip this step and say, well, in the end, I'm just going to change my y's to x's. So why don't I just start off by just putting an x here to begin with? Let me show you why you don't do that. Just real quick. You're trying to be tricky and you're like, I'm going to save myself a step. Well, let's see what happens. You mistakenly do that. And then you say, okay, well, I need to get x by itself. And so I subtract x from both sides and I get 0 equals 1x minus 1. I add 1 to both sides. Okay, x equals 1. Here's my formula. That's not a formula. That's nothing. That tells me there's 1 point. And what this has just done, if you notice, what you have just done by doing this, by trying to be clever, what you've done is you've just said, when, for what input value do you get out the same input value? That is not an inverse of anything. You have not found a formula. All you've done is you've said, when, for what number can I put into this function that gives me back the same thing? And we found that it's the value 1. When you plug a 1 into here, 2 minus 1 does give me 1. It gives me the original thing back. So that's a different thing that you're doing. You will mess up completely if you start off by saying, oh, I'll just skip that last step. No. When we're finding an inverse, what we have to do is say, okay, the output is not necessarily the same thing as the input. So let's give it a new name. And then you go through and you find a formula that gives you back your original input. In other words, you solve for x. And now you have a formula that does that. And we could verify that, yes, that's true. And so now, if necessary, which is not always necessary, we could leave it like that. But in the quiz, I ask you to write it in the form. I tell you, find a formula for this. And so I expect that you do something like this. And then in the end, you say, oh, nah, he's being tricky. He just wants me to rename it to X. And so there you go. Way over today, 20 minutes over. And actually for me, that ain't bad. It's still so, but we'll see. We'll see if, now check this out. We'll see if the linear trend continues. Day 1, I didn't go over at all. Day 2, I went over by 10 minutes. Day 3, I've gone over by 20 minutes. And we can see that this is on a line. Y equals 20x. And it might be the case that that continues or whatever. And it might not be. And this is why we want to, sometimes we'll say, well, this model is only valid from say day 0 up to day 3. It might not continue to be valid everywhere. So we'll want to restrict the domain and say the domain of this function is good from 0 to 3. So anyway, all right.